Imagine being trapped in Plato's cave.
Right.
Just, staring at shadows on a wall your entire life, trying to piece together how the real world works just from those flickering shapes.
It is a pretty classic philosophical problem.
Yeah, and for years, that is essentially what our most advanced artificial intelligence systems have been doing. I mean, large language models have been staring at the shadows.
Because text is a lossy compression of reality.
Precisely. It is a brilliant human invention, but it completely misses the high-fidelity physics, the complex geometry, and, well, the raw causality of the physical world.
And we're hitting a very hard pragmatic ceiling there.
Right, because high-quality text data on the internet is finite. So to step outside that cave, we need native multimodal models where the visual signal is treated as a first-class citizen right alongside language.
Which is incredibly difficult to build.
It is. But welcome to this custom deep dive where we are taking you through a milestone 39-page empirical study from Metafair and New York University.
Published on March 3, 2026.
Yeah. It is titled Beyond Language Modeling, an exploration of multimodal pretraining. We are going to unpack the mechanics of how researchers are building a unified brain, basically from scratch.
And building from scratch is really the operative phrase here.
Why is that distinction so important?
Well, standard industry practice has typically involved taking a massive, already pre-trained language model and awkwardly bolting a vision encoder onto it.
Like an afterthought.
Basically, yeah. But the fundamental problem with that approach is that it introduces massive confounding variables.
How so?
When you bolt systems together post-training, it becomes mathematically impossible to disentangle what the model is learning from the new multimodal data versus the latent knowledge it already inherited from its language phase.
Well, that makes sense. The data gets muddied.
Right. So to solve this, the researchers utilized what they call the transfusion framework. They trained a single, unified model entirely from the ground up, teaching it language and vision simultaneously.
I want to make sure we understand the mechanics of that simultaneous learning. Because, language and vision are structurally very different.
They are completely different signals.
So how do you train a single architecture to understand both predicting a word and processing an image frame?
They employed two distinct objectives within the same framework. For the language processing side, they used standard next token prediction.
Which is autoregressive.
Right, just predicting the next word in a sequence. But for the visual processing, they used flow matching, which is a form of diffusion.
Okay.
Rather than predicting a discrete token, the model predicts a continuous velocity field to denoise visual latence.
And how do those two very different processes not just crash the system?
They applied a hybrid masking strategy. Language uses a standard causal mask, meaning it only looks backward at previous words.
The standard stuff.
Yeah, but visual data uses a blockwise causal mask. That allows the tokens from the same image frame to attend to each other bidirectionally, so the model can grasp the entire image context at once.
Okay, so we have a unified framework processing two different types of signals. But if we are building a brain from scratch to process both text and the physical world, the first major structural challenge seems to be finding the right eyes.
The visual representation, yeah.
Right. We have to translate the visual world into a format that transformer architecture can actually digest. And historically, models seem to require two separate sets of eyes.
Yes, one for understanding and one for generation.
Yeah, like using one system for answering a question about an image and a totally different representation, typically a variational autoencoder, for actually generating new images.
The VAEs.
Right. Doesn't forcing a single model to do both visual understanding and generation just make it mediocre at everything?
You would intuitively think so, but the data from the study proves otherwise. The researchers evaluated a broad spectrum of visual representations to find out what works best.
What were they comparing?
They compared those variational autoencoders against representation autoencoders, or RAEs. Specifically, they tested an RAE utilizing a semantic encoder called SIGLIP2.
Let us pause there for a second. The difference between those two types of encoders feels central to this. Can you break down why an RAE and a VAE operate so differently?
Sure, think of their primary goals. A variational autoencoder is designed to compress an image into a smaller mathematical space and then flawlessly reconstruct it, pixel by pixel.
So its priority is perfect visual fidelity.
Yes. A representation autoencoder, on the other hand, is optimized to capture the semantic meaning of the image.
Meaning over pixels.
Right. It cares less about the exact placement of every single pixel and more about the underlying concepts that this is a dog, It is running. It is in a park.
Oh, I see. And because the RAE focuses on meaning, its output maps much more cleanly onto language.
Because language is entirely about semantic meaning.
That makes a lot of sense. So how did the RAE perform when put to the test?
The results demonstrated that a single SIGLIP2 encoder definitively beat the alternative across the board.
In both categories.
In both. Using that one unified RAE encoder, the model excelled at visual generation benchmarks. Simultaneously, it achieved superior scores on visual understanding tasks.
And what happened to the text capabilities while it was doing all this?
All of this was accomplished while keeping the text perplexity perfectly stable compared to a text-only baseline.
Oh, that is impressive. But what about removing the encoders entirely? Like just feeding the model raw visual data?
You mean raw pixels?
Yeah. If the goal is to observe the physical world directly, wouldn't raw pixels be the purest signal?
They actually tested that. The researchers patchified images into 14 by 14 tokens containing flattened, raw RGB values.
Yeah.
The interesting outcome was that learning directly from raw pixels achieved the best text perplexity of all the visual representations.
Wait, really? It was that compatible with language?
It was highly compatible. However, it lagged behind the semantic encoders in generation quality. So the overarching takeaway is that utilizing a single RAE-based encoder vastly simplifies the overall architecture. You eliminate the overhead of dual representations without sacrificing performance.
So we have successfully given the architecture a single, unified set of eyes using that representation autoencoder.
Yes.
Now we need to look at its diet. When you feed a model a massive mixture of raw video, paired images with text, and standard web text all at once, there is an inherent risk.
The modalities fighting for computational brain space.
Right. Does adding all this heavy visual data degrade the language modeling capabilities?
To test this, the researchers conducted controlled experiments, training models on 1 trillion tokens.
That is a massive scale.
It is. They compared a baseline of pure text tokens against mixtures of text tokens combined with multimodal tokens.
And did the text performance drop?
The findings show that multimodal data minimally impacts text performance. In fact, when they mixed pure text with raw, unlabeled video, the model achieved a perplexity score that matched or slightly outperformed the text-only baseline.
That is fascinating. Raw video data is completely compatible with reading and writing text.
It goes even further than compatibility. They discovered a positive synergy.
Synergy in what way?
When they added text tokens to a fixed vision budget, the image generation quality consistently improved.
Oh, wow.
Yeah, the language data seemed to anchor the visual concepts, making the model better at rendering coherent images.
But looking closely at the data composition charts in the paper, there is a specific anomaly that stands out to me.
Which one?
The charts show that mixing standard web text with metaclip data, which consists of standard image caption pairs, actually degraded the text perplexity slightly on out-of-distribution text compared to the raw video mixture.
That is a very astute observation.
Why would adding text captions hurt the overall language skills when adding raw video does not?
The researchers dug into the structural math of those captions to answer that. The degradation stems from a measurable distributional gap.
Okay, what does that mean?
They analyzed something called the cosine distance of different text sources relative to their primary web text corpus.
Let us unpack cosine distance for the listener. What is that metric actually measuring, in plain English?
In this context, cosine distance is essentially measuring how structurally alien one body of text is compared to another.
Structurally alien, okay.
Standard image captions, and particularly synthetic recaptions generated by other AI models, are structurally very strange compared to normal human writing.
Right, they do not read like a novel.
No, a caption might read, a red apple resting on a wooden table, bright studio lighting, photorealistic.
Very robotic.
Highly descriptive, but it completely lacks the diverse grammatical syntax, the nuance, and the conversational flow of general web text.
So if you feed the model too much of that weird repetitive caption data, it begins to poison the broader language pool.
That presents a tricky balancing act.
Definitely. You need those descriptive image-text pairs so the model learns how visual concepts map to words, but you do not want those robotic captions destroying its ability to write normal sentences.
Right.
How did they resolve that interference?
They decoupled the training data based on the specific capability they wanted to improve. They found that different image text sources affect capabilities differently.
For example?
Synthetic recaptions significantly improved visual question answering the model's ability to analyze an image. On the other hand, the high aesthetic Shutterstock data improved the quality of text-to-image generation.
So they just separated them.
By utilizing standard Metaclip data primarily for image-to-text tasks and the high aesthetic data for text-to-image tasks, they captured the strengths of both.
That is a really elegant solution. It optimizes generation and understanding without constantly exposing the core language engine to disparate, unnatural text structures.
It works remarkably well.
Okay, so the model can smoothly process and generate text and static images without cross-modality interference. But reading a static image is one thing.
Navigating a three-dimensional physical space is entirely different.
Right. Does this architecture actually understand motion and causality? This brings us to the navigation world model setting of the paper.
In the navigation world model setting, the objective is to test predictive physics.
How do they test that?
The model is given 4 context frames from an egocentric camera as if it were looking through a person's eyes, along with a specific text action.
And then?
It is then asked to predict the subsequent 8 visual frames.
Oh, wow.
And because of the unified transfusion framework we discussed earlier, the researchers framed this task as predicting a future visual state conditioned on a language action.
And they did this without introducing any special adapters.
None at all. No structural modifications to the model.
So to make sure I'm visualizing this correctly, is it kind of like a film director working with a storyboard artist?
That is an interesting way to look at it.
Like you hand the artist the first 4 panels of a scene, along with a script that explicitly says, get out of the shadow.
Right.
And the artist then has to perfectly draw the next 8 frames, maintaining the exact physical consistency, the shifting lighting, and the spatial geometry as the camera moves out into the sun.
That is an excellent analogy. In fact, that specific natural language prompt, get out of the shadow, was an actual zero-shot test conducted in the paper.
No way. Really?
Yes, alongside standard directional keyboard controls. The model successfully generated the subsequent frames showing movement out of the shadow.
What I find most incredible about this phase of the study is how the model actually acquired this predictive physics capability.
You might assume they had to feed it endless terabytes of specific navigation data.
Yeah, to teach it how a camera moves through space.
They tested that assumption. The researchers compared models trained on massive amounts of domain-specific navigation data against models trained on a broad mixture of navigation data and general multimodal data.
And what did they find?
The capability to predict physical trajectories did not primarily come from scaling up the specialized navigation training.
The performance actually saturated when the training diet contained just 1% of that domain-specific navigation data.
Adding more specialized navigation data beyond that 1% yielded negligible gains.
So where did the skill come from?
The model learned to navigate and predict accurate physical motion primarily from its general pre-training.
From the general data pool.
Specifically, ingesting vast amounts of raw, unlabeled video is what drove the performance.
That is staggering.
The semantic understanding of physical movement, lighting, and spatial causality transferred directly from watching millions of hours of general video data.
That base allowed the model to execute free-form language commands in a zero-shot capacity, having barely been explicitly trained on navigation tasks.
It is a profound finding.
Which brings us to a massive logistical question. If this single unified model is simultaneously performing autoregressive text generation, high-fidelity visual diffusion, visual question answering, and complex physics prediction, how does its internal brain manage the load?
That leads to an architectural shift away from dense neural pathways.
Right, moving toward a mixture of experts' design. What led them to that design? What is the fundamental scaling asymmetry they discovered?
To understand the shift to a mixture of experts, or MOE design, we have to look at their IsoFLOP analysis.
Can you explain IsoFLOP?
The researchers needed to figure out the mathematical laws governing how language and vision scale. In an IsoFLOP analysis, you systematically sweep through different model sizes and different token counts, but you keep the total computational budget fixed.
So you are asking what the optimal size is for a strict budget.
Yes, given a strict budget of computing power, what is the mathematically optimal size for the model, and how much data should we feed it?
And the mathematical outcomes for the 2 modalities were totally different.
Fundamentally different. They discovered a severe mathematical asymmetry between vision and language.
In what way?
Language is parameter-hungry. Its scaling behavior follows a trajectory where it requires a massive, complex internal architecture to capture all the nuances of grammar and abstraction.
And vision.
Vision is incredibly data-hungry.
Mm-hmm.
It requires a relatively smaller internal architecture. but it needs to see an overwhelming volume of examples to understand visual concepts.
So in a dense model architecture, where every single parameter in the neural network activates for every single token processed, this asymmetry creates a structural dilemma.
A massive one. You cannot physically optimize for both at the same time.
Because if you scale the model up to 1 trillion parameters to satisfy the complex needs of language, the ratio of vision data required to train that massive architecture becomes overwhelmingly disproportionate.
You are forced into a severe compromise in a dense model. You either drastically undertrain the vision modality, leaving it starved for data,
Yeah.
or you expend an excessive, wasteful amount of compute overtraining the language modality just to keep the model balanced.
Which is why a mixture of experts architecture is necessary.
Right. It replaces dense universal feed-forward networks with multiple specialized subnetworks, or experts.
So for each incoming piece of data, a routing mechanism dynamically selects only the top few experts to process it.
Instead of the whole brain lighting up for every single word or pixel, the router directs the problem to a specific, specialized department.
The routing behavior they observed in the study was particularly fascinating.
It was. Even though the researchers applied an auxiliary loss function designed to force uniform utilization across all the available experts, the model naturally developed distinct modality specialization.
So it organized itself.
By tracking the routing preference across held-out text and image tokens, they observed that the model naturally allocated significantly more experts to text tokens than to vision tokens.
And that emergent routing behavior perfectly mirrors the IsoFLOP scaling laws they derived.
Exactly. Because language is parameter-hungry, the MOE framework dynamically grants it access to a massive number of parameters.
And because vision is data-hungry but requires fewer parameters, the router efficiently channels the visual tokens through a smaller, dedicated subset of experts.
The structural flexibility of the mixture of experts design harmonizes that deep scaling asymmetry. It allows two fundamentally different learning behaviors to coexist efficiently within a single unified model.
To synthesize this journey for you, the listener, the study we unpack today demonstrates a viable mechanical path to building native multimodal foundation models from scratch.
It is a major leap forward.
By moving past the isolated shadows of pure text, the researchers proved we can integrate the physical world. They showed that utilizing unified representation autoencoder visual encoders outperforms traditional reconstruction methods.
And they revealed how to balance data diets by objective.
Yeah, keeping robotic captions from grating natural language. And crucially, they demonstrated how leveraging a mixture of experts architecture accommodates the severe scaling asymmetries between parameter-hungry language and data-hungry vision.
The result is a system that processes human abstraction and physical reality in tandem.
We will leave you with a final thought to mull over, rooted entirely in those navigation world model findings. We established that the model learned the literal physics of navigation, such as how spatial geometry shifts when moving out of a shadow.
Right.
It did not learn this by being strictly taught domain-specific rules. It learned this simply by observing 1% instruction and 99% raw, unlabeled video.
Which is an incredible ratio.
It is. If an architecture can extract complex spatial geometry and causality merely by watching the physical world pass by on a screen, what other fundamental rules of physical reality are currently hiding in plain sight within raw video pixels, just waiting for the right architecture to watch and learn? Thank you for joining us on this deep dive into the science behind multimodal pre-training.